So we've seen how to add vectors, and we've learned about the dot product, which is a way to multiply vectors. And now we have another type of product called the cross product. And this is another way to multiply, in a way, some vectors. All right? So when we're working with vectors, it's useful to find vectors that are orthogonal to each other. And this creates something called a vector space. And those orthogonal vectors become our kind of fundamental foundational vectors. So in order to do that, we will need something called a cross product. Okay, well, first let's define some vectors in space. We got two vectors, u and v. And they have an I component, a j component, a k component. All right, and so here they are in ijk form. The cross product of these vectors can be written like this. We have u2v3 minus u3v2 times I minus u1v3 minus u3v1j plus u2v1 plus or minus u2v1. Okay, well, you're never going to remember that, right? That's a little bunch of gibberish. Well, let's see if we can figure out where that comes from so we can make some sense out of it. So notice that when we take the cross product, we end up with another vector. So this makes a cross product something we call a vector product. Remember, the dot product gave us a scalar. So this is useful for different purposes. Well, let's back up here. One thing we need to look into is something called a determinant. So when we have a matrix, so a matrix is an array of columns and rows. And so a matrix is just something like 2, 3, 4, 5, 6, 7. So there is a matrix. This is a 2 by 3 matrix because there's two rows and 3 columns. Well, when we have a 2 by 2 matrix, we got something called a determinant. And this only happens when we got square matrices. So the determinant is a special number that's used for quite a few things, finding inverses and such. And we're just kind of scratching the surface here of matrix algebra. All right, so we're not going too deep here. But if you would take a class called linear algebra, you will do a whole bunch more with matrices and vectors. Kind of interesting stuff. So when we have a matrix that's a 2 by 2 matrix, the determinant is defined like this. Now we write it like this. We take the matrix and we put these vertical bars. Those vertical bars mean determinant or find the determinant. Find the determinant. Okay, that's what these vertical bars mean. They look like absolute values. And the determinant is defined as A times D minus B times C. Okay, so A times D coming from this diagonal going down to the left minus B times C going the other way here. Okay, so that's called the determinant. Let's try it out. Try finding the determinant here of this vector. So we got 2 times 5 minus 4 times negative 3. And that's 10 minus negative 12, which is 22. Now, I know that doesn't mean very much to you right now, but that's the determinant. Okay. If we have a 3 by 3 matrix, things will get a little more complicated. Okay, what we're going to do is, here's our definition first of all. We've got a 3 by 3 matrix. We'll define this A, B, C, D, E, F, G, H, I. And it turns out that we're just going to have 3 different 2 by 2 matrices and find the determinant of that. So we're going to break it up. And so we break it up like this. We're going to take A, and we're going to multiply that times the matrix of the determinant, I should say, of E, F, H, I. See that? Then we're going to take, let's take B. See that B there? And we're going to multiply that times the matrix of DGFI, or DFGI. Okay, so we see how we take those leftovers. So the B, we kind of ignore the the B row and the B column. By the way, these are columns up and down, and rows are horizontal left and right. Okay, and the leftover gets to be that determinant there. Okay, plus we're going to have C, and we're going to multiply that by the determinant of DE, GH. Okay, so again, we kind of block out the things in the C column and the C row, and we find the determinant of that leftover matrix. Okay, so that turns out to be, all right, when we find those matrices or those determinants, we have EI, my bad, times FH. Then we have DI, I don't know my alphabet, times GF. Oh, that's a typo there, isn't that, huh? So that should be DI times GF. Let's fix that typo. Should be G or FG. And then we have DH time or minus GE or EG. Okay? And there we have it. Okay? So you can memorize this, or we can just break it up like this. It's probably a lot easier to break it up. This is a generalized way to do this. Okay? So now notice, by the way, notice that the signs alternate. So this is positive A, negative B, positive C. So that's important. Well, let's find the determinant here. So we're going to take the 2 times the determinant of 0, negative 1, negative 2, 3. Minus, and let's take 3, and we'll take these leftover ones. Ignore this row and column here. The determinant of 4, negative 1, 5, 3. Plus, and now we're going across the top here. Negative 2. So negative 2 times the determinant of the leftovers here. 4, 0, 5, negative 2. Okay? And so that's going to be 2 times, now the 2 by 2 matrix is going to be 0 times 3 minus, here, let's go ahead and multiply these. 0 times 3 is 0. And then negative 2 times negative 1 is positive 2. Minus 3, and our determinant here is 4 times 3 is 12, minus 5 times negative 1, which is negative 5. Plus negative 2, or minus 2. 4 times negative 2 is negative 8, minus 5 times 0, which is 0. And so this comes out to be 2 times negative 2, which is negative 4. This is going to be 3 times, this is 12 plus 5, 17. 3 times 17, I think that's 51. And that's going to be minus, actually, right? Okay. So minus 51. And then negative 2 times negative 8 is going to be positive 16. And last but not least, we've got, let's see, negative 55 plus 16. That's going to be what, 39? 55 minus 16 is 39, negative. I think we got it. All right, well, that's the process. That's how we find the determinant of a 3 by 3 matrix. So the cross product goes like this. We had that crazy formula, but it actually just ends up like this. If we have 2 vectors, U and V, we're going to make this thing, we'll call it a pseudo matrix. It's not really a matrix, but we're going to write our standard vectors I, J, K, those along the top here, okay? And then we have our U vector and the V vector, okay? So those will go down here, okay? U and V. Then when we take the cross product, Okay, or if I'm sorry, we find the determinant of this. So the cross product is defined as the determinant of this 3 by 3 matrix. Well, we're going to take the I times the determinant of that, then the J times the determinant of those two right there, then the K times the determinant of those four there. And that's where that crazy formula comes from. So you can memorize this formula, but it's actually a whole lot easier to make this matrix. So let's try this out. So this cross product is the determinant, and we're going to have I, J, K. And we're going to put our vectors. We have U. Okay, our U vector here is going to be 1, -2, and 1. Those are the coefficients. And then the V vector is going to be 3, 1, -1. Okay. And when we do our cross product here, okay, our determinant, sorry, but we're doing our determinant. So we have our I vector times the determinant of -2, 1, 1, -1. So that's these four right here. And then we have minus, and we're going to have the J vector. The determinant is, so now we got our J, and so it's going to come from 1, 3, and 1, -1. 1, 3, 1, -1. And last but not least, our K vector. And then that's going to be times 1, 3, -2, 1. Okay. And now we can evaluate this. So we got our I, and this is going to be, we'll have -2 times -1. That's going to be 2. Minus 1 times 1, which is 1. Determinant. -1. So multiply those. -1, multiply those, 3. So -1 minus 3. Find the determinant here. 1 times 1 is 1. 3 times -2 is -6. So 1 minus -6. Watch out for those negatives. Okay, and that's going to end up being 1i. This will be minus -4, which is plus 4j. And this will be 7 plus 7k. There you go. Okay, that is our cross product. Now a question we might ask is the cross product commutative? In other words, if we flip it around, we get something different. Well, let's try it out. We've got ijk, and we've got v dot u. So v is going to come first. So 3, 1, -1. And u is going to come second. 1, -2, 1. Okay. And let's see what we get. So we get j. Nope, sorry, let's start with I. We'll make these vectors, put a little hat on them. Or a little vector arrow would be fine too. So we have I times the determinant of 1, -1, -2, 1, minus j times 3, -1, 1, 1, plus k times 3, 1, 1, -2. And this is going to come out to be 1 minus, multiplying here. So 1 times 1 is 1. -2 times -1 is 2. So 1 minus 2 is -1. 3 times 1 is 3. 1 times -1 is -1. 3 minus -1 is 4. 3 times -2 is -6. Minus 1 is -7. So this is going to be -7. Okay. Well, did we end up with the same thing? We actually ended up with the opposite. You see that? So we have -1i minus 4j minus 7k. Well, one more interesting thing is, what if we do V cross V? So let's try that out. So we have, make our matrix here. We have I, J, K. And we have V is 3, 1, negative 1, 3, 1, negative 1. And so if we work this out, we've got our I, 1, negative 1, 1, negative 1. So remember, we block out this column and row. There's our matrix. Now J, we're going to block out this column. We'll have 3, negative 1, 3, negative 1. And it's minus because it alternates. Oops. And then plus our K vector. We block out this row here. And we got 3, 1, 3, 1. And with that, we do our determinant for our two variable matrix. And we end up with 1 times negative 1 is negative 1 minus negative 1, which is 0. 3 times negative 1 is negative 3 minus negative 3, which is 0. 3 times 1 is 3 minus 3, which is 0. And what do you know? That's just our 0 vector. We can write it like this, 0 with a vector if we want. All right? That's the vector 0, 0, 0, 0. All right? Well, that's how we find the cross product and some properties of that. Let's look at a few more properties and we'll wrap this up. So some useful properties of the cross products are kind of like this. We've got 3 vectors in space. Now notice these are space vectors here, not two-dimensional vectors. This doesn't work with 2 dimensions, okay? But U cross V is the opposite of V cross U. We do have our distributive property there. Okay, so this is distributive. Okay. We have scalar, the associative property here with a scalar. So C is scalar times U cross V is C times U cross V, or U times C cross V. If we multiply U times a 0 vector, that is equal to 0 times U vector cross, I should say, which is the 0 vector. And U cross U is also 0. Okay. And if we have this, if we take the dot product of V cross W, then that's U cross V times the dot product of W. All right. You don't need to memorize those, but just kind of, if you take a more advanced class, you'll see those. But it is important to notice that it is not commutative. So the cross product can't be switched around. Okay? That's a very interesting fact. So the little property we care about, okay, U cross V is orthogonal to both U and V. So it gives us a new vector that is orthogonal to the 2 original ones. Okay? The magnitude of U cross V is UV sine, and the magnitude of V sine theta. If U cross V is 0, if and only if these are scalar multiples of each other. Okay, so that's useful to know. If we have 2 vectors, we'll only get 0 if one is just a multiple of the other. Because notice we saw that V dot V, or V cross V, sorry, was 0, or U cross U. Okay, so if U cross U and V they look different, but they're 0, that just means one is a multiple of the other. Okay, and got a little area parallelogram. Well, what we really care about here is this one here, all right, and that's the main thing we're going to care about here. So if we use these vectors here to find, and U cross V to find an orthogonal vector, and we can verify that it's orthogonal, then we have what we call a basis for a vector space. Well, U cross V, let's do that, all right. U cross V is going to be the determinant of this IJK vector, or matrix. And we'll put on our coefficients, 1, negative 2, and 1. And the coefficients 3, 1, negative 2. And so that equals I times the determinant of negative 2, 1, 1, negative 2, minus, don't forget to change those signs. They alternate. And we're going to use 1, 3, and 1, negative 2. So we cross out the J row in the J column. All right, we get 1, 3, 1, negative 2, plus, and we ignore the K column, and we have K times the determinant of 1, negative 2, 3, 1, which gives us, we've got negative 2 times 2, that's 4, minus 1, which is, well, I'll just write it as 4 minus 1. Minus, and we've got negative 2 minus 3, plus 1 times, 1 minus, 3 times negative 2 is negative 6. And that gives us 3i, and this is negative 5, so plus 5j, and this gives us plus 7k. There's our new vector. So this is u cross v. All right, let's call that w. And so we'll check our dot products. W dot u is, remember, we're going to multiply the coefficients. 3 times 1 plus 5 times negative 2 plus 7 times 1. So we're multiplying coefficients times coefficients. And that gives us 3 minus 10 plus 7, which is 0. And then if we do w dot v, so by the way, that means they're orthogonal, right? So w and u are orthogonal. W and v would be 3 times, now we're using v here, so this 3 times that 3, 5 times 1, so plus 5 times 1, plus 7 times negative 2. And that equals 9 plus 5 minus 14, which is 0. So they're orthogonal also. So W is orthogonal to both of them. Well, there you have it. That's a cross product, and we'll leave it at that. And it's not going to be on the AP test, but good to have some exposure to.